This is a taster for an introduction. So by its nature, it's going to be fast and furious, and don't regard this as a complete catch-all sort of training session. But it will give you a flavour of some of the things that, if you do come and attend the full course, we'll go over. We haven't got any of the sort of test equipment or other things we'd like to have to show you. This is what a PPM looks like. You know, this is what test tone sounds like. But hopefully today's session will give you a bit of a feel for what we do. I never really know where to start with audio, because some people have got quite a good appreciation of what audio is and some people don't. But starting right back at the beginning, you have to consider what we really mean. And sound, audio, it's the sensation of vibrating air hitting your eardrum. And that's the result of physical things happening. People clapping, trees falling over, things like that. And our intention in electronic media, be it radio or television or film, is to faithfully capture those signals, do things with them, post-production, and then deliver them to a person's home in a format that doesn't sound dissimilar to what was originally captured. So you can kind of think of an audio chain as being microphones, recording equipment, big sort of processing post-production equipment, transmitters, and punters, radios and televisions. And that is equally applicable if it's being delivered over the air via Crystal Palace and your television, or whether it's coming via the internet, via the iPlayer or something of that nature, or whether you're taking it home on a DVD to watch. Although those delivery mechanisms are all different, the practice and the principles of audio remain the same. The first thing to think about really is frequency. You're no doubt aware that you can hear sounds from very low, very low notes, all the way up to very high frequencies. And other creatures can hear things much beyond where we can hear. So a dog whistle to you sounds silent, to a dog is a loud screech of a noise. Typically, a person can hear from down in the few tens of hertz, a very low hum, all the way up to 20 kilohertz if you're not in your middle age, and that's the kind of range of frequencies we're talking about. And you can see on there I've got a couple of screen captures from a digital audio package. The left-hand one is showing the waveform of a very low-pitched signal, and the right-hand one is showing the waveform of a higher-pitched signal. It's well, I've labelled them there. So the first one is 100 hertz, 100 cycles per second, and that would be a very low note, probably 3 octaves below middle C if you're musical. And the one on the right-hand side, it would be a very high-pitched note if we were talking about a musical note, 100 hertz or a kilohertz as we call it, and that's maybe 2 octaves above a middle C if you're musical. The other aspect of audio is the intensity of the sound. And again, I've got a couple of screen grabs from an audio program there. The first one, you can just about perceive that there's a waveform going on there, very low level. And then the second one is very high level. And in fact, the second one is almost as high a level as the software will tolerate. And to the human ear, one of those will sound quiet and one of them will sound very loud. Human perception of loudness is a very complicated business, and it's not just down to the absolute level of a signal, the absolute level of the vibrations of the sound in the air, but a lot of other things come into play, which we may allude to later. But if we put it all together, differing frequencies, differing levels, we can see what real audio looks like. Real audio that came off a microphone, like I've got here, and that's a recording of somebody saying, "It starts with," and you can see the 3 words, and it's an incredibly complicated waveform compared to those very simple waveforms that we saw previously. Those waveforms we saw previously were what you call sine waves, and that's a very pure note. If you've ever been in a television facility, you will no doubt have heard a test signal, which is what we see there, a sine wave, a test signal. Whereas real sound, the kind of sound that comes off a microphone, looks a lot more complicated. A huge, rich mix of frequencies and an equally rich mixture of different levels, as you can see there. Now, analog audio is all very well, and in fact, analog audio is the most important thing about what we do, because your ears are analog, and the world is analog, and the business of looking after, of capturing and post-producing and delivering audio in film and television and the media is about protecting that analog signal. It's about making sure you capture it faithfully, and it's about making sure that you turn it into a faithful analog sound for somebody to listen to at the other end of the chain. Those variations in pressure, be they the variations in frequency or the variations in level, have to be reliably captured in some way. Now, a microphone turns those pressure variations in the air into an electrical signal that's travelling down that cable there to the mixing desk at the back of the room. And that's all well and good, but if you need to record sound, that sound has to be turned into a representation on a piece of recording tape or on an SD memory card or some other storage medium. And it's how you define the difference between the pressure variations in the air and the representational system you've chosen, be that analog audio tape or a vinyl record or an MP3 file. All those things demand that you pay attention to the original audio and its foibles. Nowadays, we barely deal with any analog capture of sound. Pretty much every piece of audio capture and playback equipment you might come across is storing those audio signals in a digital format, and that's true of the camera that's recording me at the moment at the back. Through to your iPod. All the audio you come across nowadays is pretty much always analog. I bet not many of you have dealt with an analog audio cassette in some years now. So if you think about turning that analog signal, that continually varying sound pressure, electrical signal going down the cables, into something that a computer can handle, one of the things you have to appreciate is that that signal has to be chopped up into many, many, many tiny pieces that can be stored by a digital system. As we know, computers internally talk numbers, they don't talk analog voltages, and that gives rise to this idea of sampling the signal. We have to chop the signal up many, many times a second, enough times that when it comes out of your iPod headphones at the other end, it's been faithfully reconstructed back into sound that sounds good to you. As mentioned before, 20 kilohertz, 20,000 cycles per second, is about the upper limit of what most people can hear. And that really gives rise to the kind of sampling we're going to be needing. This is quite a lot of words here, but just to skip through this quite quickly. The reason it's important to pay attention to these things is because broadcasters are very hot on audio levels and compliance with the standards that they set down. It's a terrible thing for a post house if tapes get thrown back at them by the broadcaster, or if more common nowadays, if a digital file gets rejected because somebody hasn't paid attention to the audio, because the audio is too loud, or it's too distorted, or it doesn't encompass the full range of frequencies that it needs to. There's a piece on the news this morning about ITV3 who've been fined for having their ad breaks too loud with respect to their programmes, which is something my old mum still complains about. The nice thing about analog systems, when we were still using them, when we had analog audio tape recorders and such like, was that they tended to degrade gracefully. If you feed a sound into an analog recorder that's too loud for the magnetic particles on the tape to accommodate, it doesn't go pear-shaped all of a sudden. It degrades gracefully. It sounds a bit wrong, but not horrible. Whereas with digital machinery, like an Avid or a Digibeta or a VTR or any other kind of digital system you might care to name, when your sound is too loud and it hits that end stop, it sounds awful. It sounds worse than awful. The system can't accommodate the level, and it clips, and it just sounds terrible. A common measurement that you'll often hear in machine rooms and other audio places is the decibel, which is a a relative measurement between different levels of sound. You'll quite often hear somebody say, oh, the line-up tone on the head of that tape is 6 dBs too low, which means that there's a discrepancy between what the line-up tone should be and what they've been presented with, what they've measured. It's worth bearing in mind that the dB is only a fractional measurement, and it's not something that tells you anything particularly about the overall level of the signal. You often hear people say, oh, you know, the noise level in the room was 96 dBs, and actually that's meaningless. If they can't specify dBs with relation to something, that's meaningless. So moving along, this picture here, we've got the 3 meters that you'll commonly come across in television and film, and in fact any kind of professional audio application. Meters are important because broadcasters being so hot on having a correct program level, it's important that everybody talks the same language. It's important that when you say, yes, my program hits a peak of this and its average level is this and the line-up tone at the head of the program is this, that you're talking the same language as the guy in the QC suite, the broadcaster's talking. And he's not going to say, well, no, you're talking rubbish. You know, I looked at it on my meter and it's totally different. So the 3 meters I've got illustrated there are the ppm, which is what you find most commonly in Europe, in broadcast facilities, in radio and in television. And it's the kind of thing you'll see typically on an editor's desk, or in the monitoring rack in the QC room, or in the desk of the dubbing mixer. And the one I've depicted there is what they call a stereo ppm. It can show the left and right levels at the same time because it has 2 needles. And typically, when you're laying down that calibration tone at the head of the tape, that line-up tone, you'd expect the line-up tone to have both of the needles hitting the 4 mark, and you wouldn't expect program level to go much above 6. So only 8 dBs of headroom between the line-up tone and the program level, and so long as you stay within those limits, you're golden. The guy at the QC at the broadcaster won't throw it back at you. The other meter you'll see commonly as well, although not so much in Europe, but it's ubiquitous in America, is the VU meter. Does much the same thing. It has a slightly different ballistic, is the word, so the needle will tend to fly a lot quicker, which a lot of people think makes it harder to read, because the needle will flick up to a level and drop back very quickly, whereas in the ppm is a weighted response. The needle will flick up quickly to a level, but then drop down more slowly. So if you're QCing the tape, if you're checking the program back before it goes out, you have a much better chance of catching those peaks, and that's why the ppm is called the peak program meter. It has a different ballistic to the VU meter. The VU meter is just a brutally honest measurement of the audio energy coming off the tape or coming off the cable or the signal that you're measuring. And then the final one on the right there is a digital meter, and you see those commonly on digital VTRs. So on the front of your digibeta machine or your HD cam machine, that's the meter you'll see. And it's slightly different in that, well, it's an electronic display. It doesn't have a mechanical needle. But it shows us absolute digital level. It shows us the numbers that are stored on the digital tape. You can see there's a marker at the -20 position, and then another marker at the -10. And in Europe, by common consensus, our line-up tone will be put at -18 dBFS. That meter uses a measurement system called dBFS, which is very common. So in terms of where you'll see and where you'll use those meters, the ppm is the one that is really the most useful. You do see fancier kind of modern digital meters, but really when it comes down to it, audio guys like ppms. And I've given you a bunch of figures there as to how the scales on the different meters relate to each other. The 4 on the ppm with a needle standing dead upright, vertical, is our line-up tone. On a VU meter, the line-up tone is at -4, because the VU meter has a different scale. And on the digital meter, as mentioned, the line-up tone is at -18. Although that's not universally true, the Americans use -20. It's a little bone of contention when you're sending tapes across the Atlantic. Everything that either generates or records digital audio will allow you to set test tones. Avid's range of products, rather bizarrely, default to -14 for their test tone. So if you're doing a layback from an Avid and you're using the Avid's internal tone generator, then it's always best to check that and make sure the Avid has been set for -18 test tone. And then there's just a little historical reference there at the bottom. If you think about the way that digital systems store audio as numbers on the videotape or in the memory or in the computer file, the analogy to that in the old analog systems was a signal strength on tape, a magnetic flux density on tape, and in case you wondered, 160 nanovabers per meter squared is the magnetic field strength for line-up tone on old analog tape, but not one to be remembered. Now, talking about getting signals in and out of equipment, the two most common styles of connectors you'll come across in pro facilities are the Canon XLR, which is the one at the top, and the B-gauge audio jack, which is the one at the bottom. There is another connector, the 1/4" jack, which looks a bit like the B-gauge jack, but that does tend to come more from the domestic and prosumer end of the market, although quite common in music recording. But in television facilities, the majority of the connectors you'll come across are the Canon XLR and the B-gauge jack. The XLR is a very robust connector used for microphones. There's one there, as well as the inputs and the outputs on VCRs. And a quick thing to remember, and if this is the only takeaway you take with you, it'll be good, the pins on the XLR point in the direction of signal flow. So the connector on the right, the male XLR, is an output. You'd expect audio signals to be coming out of that connector. And the connector on the left, the female XLR, the one with the holes, would expect to receive signals. It's an input. So when you're looking at the back of a piece of equipment, or when you're getting ready to plug something up, if you remember that the pins point in the direction of the signal flow, you won't go far wrong. The B-gauge audio jack, or the GPO jack, because it was originally invented by the post office between the wars, is the same jack for both ins and outs. In fact, it fits more commonly with an audio patch panel, which, if you've been into any machine rooms, you will have seen an audio patch panel. The audio patch panel is a way of you being able to make connections between equipment without having to wander around the back of the equipment cabinets and plug up on the back of the equipment. It also means that all your ins and outs are concentrated in a small physical area on the front of your patch panel, and it's very easy to switch things around. So you know, today Avid 1 might have been capturing sound from VT1, but later in the day they've got some different tapes come in and they need to get VT2 into Avid 1. So it's trivial to move the patching cables on the front of the jack field so that now Avid 1 is being plugged to VTR2 rather than VTR1, as an example. Because patch panels are just so useful, there's a system they employ called normaling. So if you look at that patch panel, there's 24 holes on the top and 24 holes on the bottom. The holes on the top are referred to as the source strip, and the holes on the bottom are referred to as the destination strip. And by common consent, all engineers agree this, audio signals come out of the top hole, and to connect into a piece of equipment, to patch into the input of a machine, all the inputs to the machines are on the bottom hole, on the destination strip. So if you think to yourself, signals always come out the top and they always go in the bottom, again, that's a good takeaway if you're not familiar with audio patching systems. Now, something that dawned on them years and years ago was that if you were clever and sensible about the way you laid out the equipment on your jack fields, you could do away with having to have lots of patch cords by having what they call normaling, which is like a little small patch cord built in to the actual jack field itself. So by default, source 1, which is the left-hand most hole there, that's got a signal coming out of it. Maybe it's VTR1's first output, VTR1 output 1. And destination 1, the hole directly below it, is connected to the input of Avid 1, just for example. Now, given that maybe VTR1 physically lives in Avid suite number 1, pretty much most of the time you expect to use VTR1 into Avid 1. So by wiring those jacks with a small piece of normaling wire between the two jacks, you can have it so that the signal arriving at the top jack goes to the bottom jack automatically without having to put a patch cord in there. and that's very useful. But you say to yourself, well, why on earth did you just run a piece of cable from the back of the VTR to the back of the Avid? Because there'll be occasions when Avid 1, which is on the first 4 destinations, the bottom strip, there'll be occasions when it wants to use VTR 2, the slightly fancier machine that's sitting in the machine room. And you need to be able to patch over what's going via the normaling. So the signal always comes out the top of the hole, the signal always goes in the bottom, and it's normal so that by default the signal's always passing between the two as well. But with the proviso that if you push patch cords, the little small patching cables, into the bottom strip, that will break the normaling and allow you to patch something else into that program path. You may then want to use VTR1 somewhere else, and it's still there on the top of the jack field. You can still patch it off to somewhere else. But that's normaling, and it's something that not a lot of people understand very well. I quite often have to explain that to engineers you think have been doing the job for years, and they should really understand that. And in fact, there's a couple of flavours of normaling. The kind I've described, half normaling, basically always has the signal coming out of the top jacks, the source destination, the source row. But when you patch into the destination jacks, it breaks the normaling. Fully normaling is where the signal flow is broken by patching into the top or patching into the bottom. And that's most often found in facilities where they have digital video distribution. Digital audio distribution. Digital audio distribution and digital audio distribution and analog audio distribution typically go via the same style of patch panels. Use the same patch panels to patch them, the same connection cables, and pretty much the same kind of cables between the jack fields and the back of the equipment. You also occasionally find jack fields that have no normaling whatsoever, so even if things are above and below each other, like we have in this instance, the Symphony outputs on the top and the VTR inputs on the bottom, if there was no normaling on that, then you would get no signal until you got out your patching cables and patched them in. So that's the distinction of half normaling, fully normaling, and no normaling. The other thing that's important to know about in pro audio is balanced and unbalanced. Something that confuses a lot of people, but kind of shouldn't, because it's not that hard. If you look on the back of your domestic DVD player, you'll see a couple of RCA connectors or phono connectors. The audio out the back of your DVD player is an unbalanced signal. It just has 2 connections to carry the left and 2 connections to carry the right. But if you look at the back of your Digibeta machine, you'll notice that the audio 1 connection has got 3 pins, and it uses a differential system where you've got a hot and a cold conductor which carry the audio signal, and then an earth screen connector which sits electrically midway between those 2 signals. And what this means is, you say to yourself, well, surely you just use, 50% more copper for every cable you ever use, or you're just using, more pins in every connector. But the reason we do this is that by using 2 conductors to carry the signal and a screen earth, we can reduce electrical noise induced on the line. So if you imagine you've got a VTR up in the edit suite, and it's being used to dub to another VTR down in the machine room, maybe a cable run of 50 or 100 meters. That piece of cable is like a big aerial. It picks up, radio 1 and everything else that's present in the air, and some of that might find its way onto the recording. However, by using a twisted pair cable, using this hot and cold system with the earth screen return, you know that in each of those signal legs, the noise will be induced in exactly the same quantity. You'll get the same amount of interference on each of those legs. When the signal gets to the other plate, the other end of where it's going, the other end of the cable, the machine room end, the way the balanced signal is received in the receiving piece of equipment, the VTR or whatever, it inverts one leg of that signal and adds them together, thus inverting one leg of the noise and adding it to itself and cancelling it out. So you get very good noise rejection, and this mechanism is referred to as common mode rejection. And in fact, it's not just audio signals that use balanced systems, common mode rejection to get rid of noise. You find balanced signals relying on common mode rejection everywhere. Serial control going to your PC, network cabling, everywhere you find balanced signals, because it's a very, very good way of getting rid of electrically induced noise for no extra money, for no extra processing or anything like that. Balanced audio goes back a long way. I think they knew about it 100 years ago. It's not necessary when you've got your domestic CD player and your amplifier sitting on top of each other with a foot of cable between them. And it's not necessary when you're feeding the output of your iPod to your headphones. But in big pro facilities where you've got long cable runs, balanced audio is very important. But once you've committed to building your facility around best practice and having balanced audio everywhere, you find that you can't mix and match balanced and unbalanced audio without converting one to the other. Unbalanced audio, when connected to a balanced piece of equipment, will work, but you run the risk of unbalancing not only the piece of equipment you've connected to, but any other piece of equipment that also happens to be presented on the same patch panel as that. So it's a common thing in facilities where people say, Edit 1 is humming terribly today, we've got a lot of audio distortion on Edit 1, why is this? And when you dig a bit deeper, you find that Edit 2 next door, they've plugged an unbalanced piece of equipment into the jack field, and it's inducing hum all around the facility. So again, another takeaway, paying attention to balanced and unbalanced equipment and not mixing them willy-nilly. And if you do have to mix them, if you do have to plug your unbalanced DVD player into your jack field, you need to make sure you've got a balancing box, which is a small gadget that takes the unbalanced audio and balances it up, and then you can do professional things with it. The other thing you may fall foul of once you've got yourself a balanced facility is audio phase. So if you imagine that I've got a stereo signal, a nice mixed finished program ready to go to air, and inadvertently when you made the final copy of that program, the second channel, the hot and the cold conductors, were swapped over, either through a cabling fault or somebody used the wrong patch cord on the jack field, and now you've got a recording where, to a cursory listening, you can't tell that it's phase reversed. But were you to add the left and right channels together, as people who've got little televisions with mono speakers on do, all of a sudden most of that audio gets cancelled out, and you just hear the differences between the two channels. And you may have heard that on the air. It happens occasionally, where all of a sudden the program audio goes very, very quiet, and all you can hear is just a slight whisper of somebody talking, or the effects off center or whatever, and that's a phase error. Now, if we go back to our PPMs, there they are. Well, it's not shown on this picture, but commonly when you're dealing with a set of PPMs, and if you want to go and check this out and just see it for yourself, go over to Murray Pro's stand, because they're very good suppliers of PPMs. Your PPM will have a little phase light, small red LED, which when it detects that phase difference, when it detects that reversal in one channel of the audio, will light up a red light to warn you that you have a phase problem between your left and right channels, and you should investigate that further. It's easy to rectify, but can be disastrous if it makes it through to transmission. There's a few other things that can cause errors that look like phase errors. So, for example, if an ENG cameraman is shooting an interview, and he's got a lavalier mic on the person he's interviewing, or the person that the journalist is interviewing, and you've also got a microphone on the top of the camera, quite often you'll find that the kind of distances the cameramen stand away from people they're interviewing is enough to induce a half cycle of the audio to give a phase error. The other thing that often will just light the red phase light just a bit is if you have very wide stereo music. So if you have stereo music that's been mixed with a very wide soundstage, that can cause phase errors which look like you've got momentary loss, phase error on the tape. But in fact, when you've got a real phase error, when the left channel and the right channel are out of phase with each other, you get a solid LED, and you know about it. And if you feed those two signals into an amplifier where you can mono the sound, then you really will lose most of the audio when you press the mono button. So look here, this is if any of you are familiar with Avid, this is Avid's capture tool. If you're grabbing audio into your Media Composer or your Avid Mojo or whatever flavour of Avid editing product you have, this is the capture tool you see. And what I've done there is I've dropped down the box that says select my audio source, and you can see there's there's a good eight different sources for audio there. So if you're if you're an edit assistant and you've been tasked with digitizing 100 tapes, before tomorrow morning's editing shift, this is the kind of thing you have to pay attention to, because you select the wrong one and you will get no audio with your pictures. You can see that the one that's ticked at the top there is marked XLR, and that equates to the XLR connector on the back of the Avid. That's the balanced audio, the balanced analog audio. The next one down is labelled RCA, which again corresponds to the unbalanced input. Some Avids have got unbalanced inputs as well as balanced inputs, and that's the same phono connector that you find on the back of your DVD player or your prosumer equipment. Excuse me. The next one down, DNA 1394. That's a Firewire standard. And that's if you've shot, maybe you've shot all your rushes on a Z1 or some other prosumer camera, and you want to be able to copy those over the Firewire without any digital decompression, recompression. That tells the capture tool that it's looking for the audio coming down the digital cable, down the digital Firewire cable. The next one down is AES-EBU, and this is the most common digital audio standard that we use in television. Again, it uses exactly the same connectors as analog audio, the Canon XLR you see there. But this is audio that's already been digitized. It's already been turned into a digital waveform, or a bit stream, I should say. It's not really a waveform; it's a bit stream. And that's, if you had a digibeta machine, you might tell the Avid that you want to grab the audio off the AES-EBU inputs, or a DAT tape, or something of that order. The next one down, SPDIF, is a domestic digital standard, which you may well find on the back of your home theatre amp at home. That's probably got SPDIF on it. And there's a couple of optical standards, ADAT and optical SPDIF, and these are all variations on a theme, and they're the kind of things you might find on the back of sort of prosumer music, multi-track recorders, that kind of thing. And the very bottom one, probably the most important as far as a modern facility is concerned, is the SDI input, the serial digital interface. That's the digital video standard that pretty much all modern television equipment uses. And as well as carrying the standard or high definition video signal down that single BNC cable, you can also carry embedded in that serial digital signal 8 channels of audio. There are some variations on that, but if we're thinking about HD cam or those kind of standards, that's a common way of being able to get 8 channels simultaneously into an Avid. You take them over the SDI input. Not all VTRs or not all audio recorders will come. They'll all come with a subset of those standards. Thankfully, the Avid, in most configurations, has a bigger subset than you're likely to find on the equipment, so generally speaking you can get the audio in some way, but it's worth remembering that if you can, SDI is a good way to go, because it travels down the same cable as the video and you run less of a chance of things going wrong. Nothing's been touched. It's not like you've run the risk of introducing a phase error into the analog audio, so stick with the SDI if you can. Now, having said that PPMs were ubiquitous and the most common audio monitoring equipment you're ever likely to come across, as we enter our multi-channel present, with HD television, and everybody wants a 5.1 surround sound feed delivered to their home, and in fact that's been around for a long time with movies on DVD, movies on Blu-ray. 6-channel audio, 5.1 as it's referred to, is very common, and it then becomes very hard to sensibly monitor what 5.1 audio looks like on a set of PPMs. I mean, you could have 6 PPMs in front of you and you'd be able to tell what the levels were and whether they had phase errors and all that kind of stuff. But there are other things you need to find out about when you've got a big sound stage, when you've got a surround sound system. So there's the audio monitoring display of a Tektronix test set, and you can see on the left-hand side there, you've got the levels for the 6 channels, and in the case of 5.1 audio, that they run left, centre, right, and then the two surround sound channels at the back, and then there's what they call the LFE, the low frequency effects channel, and that's the big bass bin speaker that sits, under your sofa, or hidden away behind your telly or something. And then as well, we also have a stereo mix that's made inside the Tektronix as the next two bars, because I think most broadcasters appreciate that even though they're putting their program out in glorious HD with 5.1 surround sound, an awful lot of people will be watching it in SD with only stereo audio. So it has to sound good and look correct. It has to conform in both standards. So the Tektronix is very helpful in making stereo indicator of the 5.1 surround. And then on the right-hand side of the display there, you can see the phase meter, and we've gone from phase just being a single LED on the ppm meter that comes on when it's wrong and goes off when it isn't, to quite a complicated display that really does show the nature of and how complicated sound is. If that was a test tone, that would just be a straight line running diagonally, top left to bottom right. And if that was a test signal that was out of phase, it would again just be a straight line, but it would be inclined through 90 degrees the other way, and it would be very obvious to you that it was out of phase. But this is a piece of audio that was captured from a movie, and you can just see how complicated real mixed sound is by comparison with test signals. Test signals are great. They tell you that things are working, they show you level, but they don't look like real program audio. So in our complete course, we go over the Tektronix in lots of detail, because in a contemporary facility where 5.1 audio is important, it really is the kind of meter you'll find. 10 years ago, before multi-channel audio was important, and we were just dealing with stereo, or at most 4-channel for delivery, with a stereo mix on 1 and 2 and a clean M&E on 3 and 4, so that the foreign broadcaster could add his own voiceover track. PPMs and VUs and digital meters on VTRs were just fine, but that's not the case anymore. And as we move into everybody wanting delivery of 5.1 audio, you'll see things like the Tektronix WVR range and DK Audio and other manufacturers' meters that do this kind of thing to be much more prevalent. So that's really the quick run through of all I wanted to say, and to give you a little taste of what you'd be exposed to if you wanted to come on our Audio 101 course at root6. Again, I'd emphasise that whereas I've just whizzed through this, we'll have test sets, we'll have meters for you to hold and plug up and play with, we'll have connectors for you to look at and stuff like that, and it'll hopefully be a much more edifying experience.